Okay, so welcome everybody once more to the official IAU G2 online conference series, this time with warm weather around all the northern hemisphere. As usual, this is about massive stars, and today is a great honor for me to introduce our next speaker, Jiří Krtička. Hello, Jiří.
Hello.
At present, Jiří is a professor at the Department of Theoretical Physics and Astrophysics in the Masaryk University in Brno. He developed his PhD thesis entitled Hydrodynamics of the Stellar Wind between 98 and 2001 in the same university, where he has also stayed during most of his career. But he has also done short and midterm stays in many institutions abroad, including institutions in Potsdam, Munich, Tartu, Hamburg, and Glasgow. His main research activities has been mostly focused in the study of radiatively driven winds of hot massive stars, but he has also been interested in the study of atmospheres of chemically peculiar stars and outflowing disk in fast-rotating stars. If I'm not mistaken, all this mainly from a theoretical and modeling point of view. So I'm really looking forward to hearing directly from you, Jiří, about your most recent and maybe also not so recent results. So thank you very much once more for accepting the invitation by the IAU G2 Commission. Whenever you want, the floor is yours.
So thank you. Hello, everyone. First of all, I would like to thank the IAU G2 Commission for giving me the possibility to talk here about the line-driven wind massosite predictions, and of course, all of you for coming today despite this very hot weather, at least in Europe. So first of all, we all know that the stellar wind of massive stars are accelerated mainly by the radiative force in line transitions of heavy elements, but let us first look on this radiative acceleration from a slightly broader view. So the radiative force itself was brought to the modern physics by Maxwell more than 150 years ago, and it took about 30 years to experimentally detect the effects of this radiative force. It was done by Russian physicist Lebedev and Americans Nicholson and Hall. And they have to use the very precise laboratory equipment to detect this radiative force, the effect of this radiative force, because the radiative force, we cannot basically expect any effects from the everyday life. But in our physics of hot star winds, we study this effect of the radiative force causes a huge amount of mass loss, macroscopic effects, and can affect even the evolution of these massive stars. So the fact that this radiative force can be obtained only from precise experiments on Earth, but can cause huge outflows in massive stars is to me very, very interesting. So I think it's very nice that we study such a complex physics of such interesting subject. And that's, I guess, also the reason why Stenovoky called these winds, or somehow whimsically, as winds that sail on starlight. But there are more interesting, fascinating physics connected with these hot star winds. As I've mentioned, these winds are accelerated mainly by the line transition of heavy elements like carbon, silicon, sulfur, or iron. But these elements constitute just a small fraction of the stellar wind. Most of the wind is composed from hydrogen and helium. So this means that there should be some momentum transfer between these accelerated particles, between carbon, nitrogen, iron ions, and hydrogen and helium. And this is caused by collisions of charged particles. And this effect is now from the plasma physics, and it became clear that such effect can appear just in the 50s of the last century. So we have very interesting effect that is important also for plasma physics. Then we have this effect of plasma heating that comes from the asymmetry of irradiation of individual lines. And this heating was basically, or heating or cooling, depending on the line profiles or on the flux. This effect was used in laboratory to cool the matter using plasma beams, and actually it was awarded by the Nobel Prize. So we have a Nobel Prize physics already in these hot star winds. And then hot star winds are ionized. So this means they can interact with the magnetic field. So we have many interesting effects connected with the interaction of the stellar wind and magnetic field. Many massive stars come in binaries, and this means that one of these binaries can involve either in a black hole or in a neutron star. And then we have accretion on these objects from the stellar wind. So this type of accretion we cannot basically, I think, find in other fields of the stellar astrophysics. Massive stars emit a huge amount of radiation, but the winds are a relatively low density environment. So this radiation affects excitation and ionization state of the wind. And in turn, we have strongly non-equilibrium physics in the hot star winds. And last but not least, this radiative driving leads to instabilities and new types of instabilities, and that's also a very interesting, fascinating piece of physics we can study in hot star winds. But today I'm not going to talk about this interesting physics, but I am just going to focus on basically one topic, and these are these mass rates. And why these mass rates are so important, why for our community it's very important to provide mass rates for other astrophysical communities. And this can be basically understood from, for instance, from this initial mass function, which gives you the amount, the number of stars that appear during the star formation per unit of mass. And if you, of course, you know that these stellar populations are dominated by low mass stars. But if you looked really at the high mass end of this initial mass function, then you can find out that really massive stars more massive than 10 or even perhaps more than 100 solar masses do really exist. And if you think what is their final evolutionary outcome, these massive stars, if they leave any remnant, end up either as a neutron star or as a black hole. But a typical mass of the neutron star is 1.3, 1.4 solar masses. A typical mass of the stellar mass black hole is of few solar masses. And this means that most of the mass of the massive stars is lost during the evolution. And to understand this evolution, we have also to understand the mass loss that appears from the stellar formation up to the final supernova explosion. And of course, there are several ways how massive stars can lose their mass. They can lose a significant fraction of their mass during their final supernova explosion. But since many massive stars come, or maybe most of massive stars perhaps comes in binaries, also the binary mass transfer becomes important, either the mass transfer or the common envelope phase. But even single stars may lose their mass, either, for instance, during this LBV type of outbursts. In fast rotating stars, we can face outflowing disk, and these stars can lose the mass by this way. And typically, massive stars may become a supergiant in their evolution, and these stars are known for strong mass loss, which is not up to now theoretically understood very well. But today, I will focus just on one type of the stellar winds, and these are line-driven winds that appear during hot evolutionary phases of massive stars. So since these stellar winds are accelerated by the radiative force, this means we have to focus, if we want to really predict the mass of from observations, we have to focus just on this line force. And in principle, the formula for the line force or the radiative force looks pretty simple. What you have to do, just to take the opacity, multiply this by the flux, integrate over the frequencies to get the amount of energy absorbed by the wind, and if you divide it by the speed of light, you get the force. But despite this equation looks pretty simple, it's in fact very complicated to calculate the radiative force. The first point is that the radiative flux is basically given by the solution of the radiative transfer equation, and this introduces some non-local coupling into the calculation of this radiative flux. And the flux and also the opacity are strongly varying functions of the opacity of the frequency. So this means itself to calculate this integral, it becomes very complicated, and you have to integrate basically frequency by frequency to get the correct radiative force. But if you want to get muscle strength from theory, it's not enough just to calculate the radiative force. You have to put the radiative force into the hydrodynamical equations and to solve this equation. And there comes another problem because you know that these hydrodynamical equations are not linear equations, so you can worry about the problems like uniqueness, and also these are time-dependent equations, so you should worry about the variability of the stellar wind. So and if you solve this, then at the end you can somehow predict the muscle rate just from the theory. So let us look at different steps you have to do to calculate the radiative force using this equation and the muscle rate, predicting the muscle rate from theory. I said that this way of calculation of the radiative force is pretty complicated, but there is a way how you can simplify the calculation of the Sobolev, calculate the calculation of the radiative force, and this way is called the Sobolev approximation. So let us look at the line transfer. It's just in a single line, and assume that we have some expanding wind that shows this dependence of the velocity on radius. But since on this y-axis we have already the velocity, we can attribute some Doppler shift due to the Doppler effect to a given spectroscopic line. And as the wind accelerates, also the frequency at which a given line is able to absorb the radiative flux from the star should shift due to the Doppler effect. And this basically because these lines have typically finite width, we can show, or we can plot also this gray region that basically corresponds to the width of a width of a given spectral line. And now, if you imagine that we have a photon that moves from in the stellar wind from the stellar surface, then it cannot be absorbed in a given line in this white region of this graph. It can be absorbed just in this gray region, but once it leaves this region, it cannot be absorbed again. And basically, this gives you some idea how to simplify this calculation of the radiative force. So if you imagine that you have the width of this profile given just the thermal broadening, then this interacting region, which we can call the Sobolev length, is pretty short, and its length is basically given by the width of this line in the say velocity space divided by the velocity gradient, and this gives you the length of this gray region where this radiation in a given line can be absorbed by the wind. And now, if this length is much smaller than typical radius at which you calculate the radiative force, this means if you are in the supersonic approximation, that the wind speed is much higher than the thermal speed, then typically you can significantly simplify the calculation of the radiative force. You can just account for the work done by optical thick line, which is given by just the radiative force times this Sobolev length. And this should be equal to energy taken from the radiative field, which is given by the flux times the line width. And if you plug in this Sobolev line force and frequency line width, then at the end you end with the equations for the radiative force in assuming the line is optically thick, and you find out that this radiative force is proportional to the velocity gradient. So this means if you have higher velocity gradient in the wind, you get stronger line force. But that was just for optical thick line. In the case of optical thin line, you can just neglect the detailed radiative transfer and just multiply the flux and opacity, and you get the line force in this optically thin line. But this can be generalized, including some accounting for more detailed radiative transfer, and you get this formula for the radiative force, where T is now some kind of Sobolev optical depth, inversely proportional to the velocity derivative, and Q is some kind of the line strength. And now if you face optically thick line, then this t is much higher than 1, and you can neglect this exponential, and you and get the optically thick line force proportional to velocity derivative. And for optically thin lines, when t is much smaller, you can expand this exponential, and at the end you get the you can recover this optically thin approximation for the calculation of the radiative force. And already you can use this approximation to estimate the mass state from massive stars. You can just put this radiative force into the momentum equation, hydrodynamical equations for the velocity. And if you assume that you have a bunch of optically thick lines, then you should sum up the contribution of all optically thick lines. And if we plug in the photospheric flux and photospheric radius into this expression, then on the left-hand side, you already get the mass rate, the amount of mass lost by the star per unit of time, which is given by just the surface, times the mass flux per unit of surface. And this velocity derivative on both sides of equation cancels out. And you see that this mass rate is somehow proportional to the flux. And in fact, the mass rate is proportional to the luminosity or photon mass rate multiplied by this number of optically thick lines. And already from this equation, you predict that the mass rate should be somehow connected to the stellar luminosity. And of course, in reality, you do not have just a single or a bunch of optically thick lines, you have optically thin or optically thick lines. So what you can do, you can just introduce some line strength distribution function with parameterized by this Q bar, Q0, and alpha parameters, and sum this radiative force we have derived before over this line strength distribution function. And if you divide this by the radiative force due to the free electron scattering, then what you get is the line force multiplier that basically expresses this radiative force in terms of the radiative force due to the light scattering on free electrons. And then you can get this plot, which plots this line force multiplier as a function of the optical depth. So now the optical depth is not, this tau is the same as the t here. And this gives you already some hint on what are these parameters Q bar, Q0, and alpha. So when in the case when you have very low optical depths, this means that all lines are optically thin. You get somehow maximum line force, some case of the maximum line force for the ensemble of these lines, and this is described by this Q bar parameter. But as the density increases, some of the lines become optically thick, and this distribution turns down, and this place where this happens is described by this Q0 parameters, and the steepness of this distribution function is described by this alpha parameter. So this gives you some geometrical understanding of these parameters, and in this steep part of this MT distribution, you get the CAK force. So now within this CAK model, because you have optically thick, optically thin lines, some lines become optically thick, some lines may become optically thin. Now you get the more complex dependence of the radiative force on the velocity derivative via this exponent alpha. And if you look at this saturated part of this diagram, then what you can get is the wind condition. So this basically gives you for a given Q bar and for a given parameters expectation where you can expect the stellar winds and where you do not expect the stellar wind. And you already can compare this with observation. So what, for instance, you can do is that you can plot this HR diagram with evolutionary tracks, and you can put on this diagram stars that show H-alpha emission line profiles, which is some proxy of the stellar wind. And so these are these blue dots. And you can also plot stars that do not show any H-alpha emission. These are this star with red symbols. And you can overplot with this blue region, the region of the star where this simple condition we have seen before predicts the stellar wind. This is this blue region, and white region, and this part of this diagram predicts no stellar wind. So, and if you compare the location of this boundary between wind and no wind, then it nicely corresponds for distance to the disappearance of H-alpha emission in this main sequence B stars. So already quite simple approximation already gives you some testable predictions concerning the appearance and perhaps disappearance of the stellar wind. But of course, today I'm going to argue that to calculate really reliable mass of size predictions for massive stars, you cannot simply use the simple Sobolev approximation. What you have to do is really to solve the radiative transfer equation line by line, frequency by frequency, and this gives you reliable predictions for the mass of rate. And so we have to first look whether this Sobolev approximation can give a good approximation for the calculation of the line force or not. And this is already shown on this graph, which basically compares the line force compared using the detailed solution of the radiative transfer equation. In this case, in the co-moving frame, this is this black solid black curve, compared with approximate Sobolev calculations of the radiative force. This is this dotted line or this dashed dotted line. And as you can see, both in the case of optically for case of strong and weak line, this Sobolev approximation gives very good estimate of the line force in the supersonic regions, or the region where the radii in the stellar winds pretty high. So the question, if I'm saying that the Sobolev approximation gives a pretty nice approximation for the line force, why I'm saying that at the end you have to use this CMF calculation of the radiative force. And there are more reasons for that. And the first one is basically shown on this graph, which basically shows the same, in some sense, same plot as the previous one. But now on the y-axis, I do not plot the line force itself, but the ratio of the co-moving frame line force. So this means the line force calculated from detailed solution of the radiative transfer equation and the Sobolev line force. And as you can see, if you basically neglect line overlaps, if you focus just on single lines, in the supersonic region of the stellar wind, this ratio is equal to 1. And this again tells you that in this case, the Sobolev approximation is a very good approximation to calculate the radiative force. But once you include the line overlaps, and remember that's the typical case of our stellar winds we study, because these stellar winds are accelerated frequently by line doublets, and then the line overlaps become really important. And if you include the line overlaps, then now this ratio significantly decreases. And this leads to already this effect leads to a significant decrease of the mass of rate by, say, a factor of about 30%. But there are more effects like that. If you compare the flux distribution as a function of frequency from static model atmosphere, in this case, this is this black line from the elastic model atmosphere, and from global unified models with detailed co-moving frame, then you get this blue curve. And from first point of view, this curve for this particular star match pretty well. But the point is that the radiative force is given by the flux times the opacity, and in this particular case, in the case of the particular star, the region which is very important for the radiative driving, and this is this high frequency region, the stellar wind itself basically absorbs the light from the star. This leads to the decrease of this flux on this region, and leads to significant decrease of the mass loss rate, decrease of the radiative force, and therefore of the mass loss rate. So this also shows that a detailed solution of the radiative transfer equation is necessary to account for the effects like this. And there are more effects like this. For instance, if you look at the temperature distribution and at the base of the wind, then of course in the photosphere the temperature is decreasing, but then the temperature starts to increase again, because now as the wind accelerates, the winds or the lines start to see the flux from the photosphere, and this leads to some kind of heating. And this heating leads to a negative source function gradients, and then decrease the radiative force in the subsonic part of the stellar wind. And this is again a fact that cannot be simply calculated within the simple Sobolev approach. So these are the problems connected with the solution of the radiative transfer equation. But of course, there are much more problems connected. There are additional problems connected with non-equilibrium physics we basically face in these hot star winds. The point is that in the case of thermal equilibrium, the calculation of the number densities of atoms that you need to calculate the opacity is relatively simple. You simply use the Boltzmann equation to get the level population, the Saha equation to get the ionization balance, and you at the end get the number density of atoms or ions in a given level. But in the case of the hot star winds, these level populations are significantly affected by ionization or excitation processes that appear due to radiation. So this means in this case, the radiation significantly affects the level population, and this means that to get this level populations correct, you have to solve the kinetic equilibrium equations. So you have to account for all radiative or relevant radiative processes that can affect the number density of atoms in a given level. And at the end, this gives you a very complex contribution of different elements to the radiative force. So this plot taken from the paper of Andreas Sander basically gives you contribution of different ions to the radiative force, relative contribution as a function of the radius. So in this part of the graph, we are close to the photosphere. In this part of the graph, we are basically in the wind. And all these different symbols correspond to different ions. And as you can see, the contribution of different ionization states changes with the radius, because the ionization equilibrium changes as you accelerate the stellar wind, and also the contribution of given elements or individual elements change as a function of the radius, because close to the star, many lines, many iron lines are optically thick, so an iron has a huge amount of lines. So this means that close to the stellar surface, the radiative force is dominated basically by iron, but the contribution of iron decreases in outer stellar wind because the wind density decreases, and these iron lines become optically thin, and that's the time when lines of lighter elements, like in this case nitrogen, sulfur, or silicon, become important for the acceleration of the stellar wind in this part of the stellar wind. So to get this graph, to get the correct radiative force, in this case you will have to account and to solve all kinetic equilibrium equation to get a reliable prediction of the Masaryk rates. In fact, this is somehow unfortunate, because it would be beautiful if we could use just LTE approximation, because it's so simple to calculate the radiative force. And if you compare the calculation or the ionization structure you get from the LTE equilibrium and non-LTE equilibrium, accounting for this kinetic equilibrium equations, then basically the ionization state from LTE is basically never correct. And that's basically shown in this graph, which compares for a particular star the ionization fraction as a function of the radial velocity, as a function of the velocity, and different line types correspond either to non-LTE calculations, these are these solid lines, or LTE calculations, which is described by this dashed line. And different colors correspond to different ionization stages of oxygen. And as you can really see, basically in the stellar wind, the LTE approximation never, except maybe for this particular region, never gets the correct ionization structure of the stellar wind. But still, if you use this LTE level populations and assume Planck flux for the emergent radiation from the star, and you use the Sobolev approximation, then at the end you get prediction for the muscle size which are very close to the predictions of from the CMF calculations, and that's shown actually on this graph, which shows the muscle rate as a function of the stellar luminosity, and now this black line corresponds to some mean prediction from CMF models calculated with coming from radiative force and from the kinetic equilibrium equations. You see that the muscle state really somehow scales with luminosity, and these blue symbols correspond to LTE models with Planck flux and Sobolev line force. And as you can see already, this approximation looks pretty simple, gives a relatively good estimate of the muscle rate. And that's because you get perhaps a wrong ionization structure, but also the Sobolev line force is not correct, and different effects cancels out, and at the end you get relatively reliable predictions for the muscle rates. And in fact, this is a good message for hydrodynamical simulations, because in hydrodynamical simulations you basically cannot use kinetic equilibrium equations to get the estimate of the ionization structure, and it would be nice to use the LTE population, because these are much more simpler. And in fact, one can do this, but of course, one should be aware that this holds fine in Oak stars and may not be correct in other for other stars, like for instance for hotter stars. So we have seen how to calculate the radiative force from the radiative transfer equation and from the level populations of given elements, but this is not the end. This is not still enough to calculate to predict the muscle rate. To predict the muscle rate, you have really to solve the hydrodynamical equations. And for the first time, it was basically done by Castor, Abbott, and Klein, giving this CK model. And you can see the solution of their equation as a function of the radius. So this means velocity as a function of the radius. And you can see that there are several parts of this solution diagram that show either no solution, like this and this part of this diagram. Some parts show just a single solution, and in some parts, like in this part, you get actually two solutions of these hydrodynamical equations. And the famous CAK solution is the only solution which starts subsonically in the photosphere, expand to supersonic velocities, and is smooth throughout the whole part of the solution. And this is so-called critical solution. And the question is, why basically in the nature select this critical solution to and why this critical solution basically gives a good prediction, good match with observation. And one view on that was proposed by Abbott, who have found some kind of new types of waves that are connected with this CAK line force. And basically these waves in the frame of the star move inwards just below the CAK critical point, and in the supersonic region, and they move at velocities, they move outwards from the star. And from this point of view, this means that if you modify the solution in outer part of the stellar wind, you cannot basically transform or transport this information toward the the star surface. So the CAK critical point acts as some kind of informational barrier. And it was nicely compared by Achim Federmeyer and Isaac Schlossman in their paper comparing this to well-known black hole conjecture. But now in the stellar wind, the situation is somehow opposite to black holes, where in the black holes, the change of the solution does not or the change of the solution below this short-shell radii cannot change the solution outwards. We have the opposite solution. Now the change of the solution in the outer part of the stellar wind cannot simply change the solution below this CAK critical point. But this is a little bit more complicated when you account for non-sobolev radiative force, because now you get some instabilities and you do not see clearly this about waves. So you can calculate this non-sobolev line force within several approximations. But luckily it seems that at least close to the star, the effect of diffuse terms in the radiative force can stabilize the radiative transfer equation, and this can be seen in these three different plots that shows the velocity and density from hydrodynamical simulations and account for this non-sobolev radiative force. And thanks to this this diffuse terms close to the stellar surface, the solution is relatively smooth close to the stellar surface, but now the instabilities appear in the outer parts of the solution. But still, to me, this is not fully well understood how this diffuse term stabilize the solution. So I think there is still some room of the research in this field. But the typical models that predict the Mason's rate now, which are used now to predict the Mason's rate, typically do not use these time-dependent simulations, but they just solve the static hydrodynamic equations, and they have to use slightly different approach to predict the Mason's rate. So what is done in the models of Yorick Wing, and these models basically calculate the radiative force for some prescribed velocity field and compare or search for the consistent value of the total work done by the radiative force, while the models of Sander and Sundqvist, they account for the search for the consistent solution in the region of the sonic point. We do basically the same within our models, but since in our models we scale to get the convergence of the models, or to converge the models, we scale this radiative force with respect to the CAK line force. We search for the consistent solution in the region of the critical point. But at the end, this approach, which is used by the up-to-date models, is basically in some case similar to what was introduced already by Castor and Klein, and so we basically search for the smooth and consistent outflow as was done by CAK. And this approach, basically, you can see at this graph, which shows the different solution depend for different base velocities or for different Mason's rate as a function of the radius. So if you increase the Mason's rate, you increase the wind velocity, and finally you get this smooth solution, which actually corresponds also to maximum Mason's rate, which is this black solid curve, and this very nicely corresponds to CAK solution, which is described with this dashed curve. And so this means to get reliable Mason's rate predictions, what you have to do is to couple the consistent solution of the radiative transfer equation with hydrodynamic equations, and you have to do this throughout the stellar wind. So this means you have to start with basically a hydrostatic photosphere and search and look for the wind accelerations for up to the supersonic velocities with non-Sobolev radiative transfer. So this means you have to calculate some kind of global or unified models which describe both the photosphere and the stellar wind in some unified manner. This means that they account for not only for the influence of the photosphere on the wind acceleration, but also they account for the influence of the wind itself on the temperature and hydrostatic structure of the photosphere. And there are several models that can do this. Typically, they are connected with some models that are already able to predict or to determine the mass oscillate from the observations. So there are two branches of the power models, either by Gesgrafener and Wolfenhamann and by Sander. The code fast wind was used by Jon Sundqvist to predict the mass rate, and the Simevchen code was used by Alex Gormas-Matamala again to predict the mass rate. Our code is somehow independent from these, but it heavily relies on the Tilasti code, at least in the sense of the atomic models which we take from the Tilasti models. And in general, all these models predict some kind of reduction of the mass loss rates with respect to wing mass loss rate predictions, which are nowadays used typically in the evolutionary codes. And of course, in the end, what you want to do is to compare this mass loss rate, theoretical mass loss rate, with observational values. And now I cannot simply fully credit all the work done by people that try to estimate the mass loss rate from the observations. And the point is that you cannot simply use some observation features to get the mass loss rate. What you have to do, you have to calculate complex models and vary the mass loss rate in these models, and we get some varying spectral features, and that at the end gives you some estimate of the mass loss rate. So people can typically use either the shape of X-ray line profiles. More typically, you can determine the mass loss rate from the optical and UV wind line profiles. You can also use the near-infrared line spectroscopy for the estimation of the mass loss rates, or infrared and radio access. Of course, this will somehow interact with the interstellar medium, and you can also use the strength of this interaction to get some estimate of the mass loss rates. And recently, there was a huge HST and VLT project, Ulysses and G2, which basically provide a very homogeneous estimate of these mass loss rates, including the effect of clumping, which turns out to be quite important to estimate the mass loss rates from the observations. So when you use this observational estimated mass loss rate and compare this with the mass loss rate prediction, then you can get graphs like this, which basically again compare the mass loss rate as a function of the luminosity. Again, the solid line corresponds to the predictions from this coming flame unified models, and different symbols gives the observation values for our galaxy, large Magellanic Cloud, and the small Magellanic Cloud. You can see that the mass loss rate decreases between these three galaxies due to the different metallicities, but at the end, you can get a quite reasonable agreement between the observations and the theory. But of course, when you look at these graphs more closely, you find out that there is quite huge scatter of the observation values, and you can wonder whether this scatter is real or not. And to understand this, we basically use just one of these observation samples, the LMC sample of O stars from Hawcroft, and we basically compare the observation values with theoretical values using the fitting formula that you can get from this grid of these unified models as a function of temperature, luminosity, or in principle the stellar mass. And we calculated this ratio of the observational values and theoretical ones, And what you want to get at the end is that this should be in agreement. So you want to appear somewhere around this one line. But if you do this for individual stars, then you get pretty huge scatter of these estimates. And on average, there's some agreement, but this scatter is not something from which we should be happy. So we now tried a different approach, and we calculated tailored wind models. So basically, we use the same. Basically, we use the same wind models that were used to get this fitting formula. But now we use this model for parameters corresponding to individual stars from this Hawcroft sample. And what you get at the end is much better agreement. In fact, many or most of these stars appear close to one. So there's already a much better agreement, a much lower scatter when you calculate the tailored models for individual stars and do not rely on some fitting formula that was basically derived from the same models, but from some grid of the stellar parameters. And this perhaps indicates that we have to at the end calculate tailored models for individual stars, and the reason why this scatter becomes lower is that there is some variations of ionization and stellar parameters that leads to significant scatter of these observed mass rates. So in fact, some part of the scatter in this observation could be real, and at the end, one may have to calculate wind models for specific stars. So up to now, I was just talking about the effect of radiative force, about the way how we derive the mass rate, but I've basically neglected many interesting effects like the effect of thick winds or the effect of wind instabilities. But at the end, all these effects can become important when you estimate the mass rate from the theory. And during the rest of my talk, I will just focus on these wind instabilities, how they can, in principle, affect the mass rate predictions. And this can be seen already from these numerical hydrodynamical simulations that study just a box in a wind. So each box in this plot corresponds to the box in the stellar wind. The bottom part of this box, of these boxes, corresponds to the stellar photosphere. The upper part is basically supersonic, correspond to supersonically accelerated stellar wind. And each of these boxes correspond to different time step in the hydrodynamical simulations. And now this bottom row corresponds to the Eddington parameter. This gives you the wind velocity. This row gives you the wind density in a given time divided by the mean density from the simulations, and the upper row is basically the same but for temperature. So you can see from hydrodynamical simulations there is a huge structure that appear in the stellar wind. But still, when you compare the predictions for these hydrodynamical simulations with what you get from global or unified wind models, that at the end you can get a relatively reasonable agreement. It's quite surprising, but it seems to be the case, and this is shown in this graph, which again shows the dependence of the mass rate on the stellar luminosity. Now this dash or dash dot curves correspond to predictions of CMF global unified models. And this red star corresponds to this result of the hydrodynamical simulations. And as you can see, these red stars relatively closely follow the result from the simulation. So that shows that the effect of the instabilities may not be that strong on the mass rates, but still, I guess some research is still needed in this field. And finally, if you really look at these plots which compare the mass rate for different galaxies as a function of the luminosity, compare the observed values with predictions, and if you look at these low luminosity stars, then apparently the estimates from theory are significantly higher than what you get from the observations. And not even the observation with James Webb Space Telescope in infrared gives some clear clue to what happens in this region, whether really the simulations overpredict the reality, or if the muscle rates are in fact correct, and we are not able to somehow get correct or realistic muscle rates from observations. And perhaps there is also the place where the instabilities may play some role. And the point is that once the instability appears in the stellar wind, it leads to some shocks, and these shocks heat the wind material to very high temperatures. And the wind cooling now depends on the density and on the cooling function. So you can write down this cooling time, which is inversely proportional to the wind density. Of course, as when you have high density, then the cooling time becomes slower. And of course, it's also proportional to the cooling function. And this means you predict very long cooling times, either at very low wind densities or when the cooling function is low. This means for very low luminous or very low metallicities. And this is basically compared in this graph, which compares the wind simulations for high density of supergiant and low density of dwarf. And now this graph basically shows just the temperature of the wind, and the yellow graph, yellow part of this graph, symbols correspond to very high temperatures. And you can see that just at these high temperatures, only a small fraction of this supergiant wind appears at these high temperatures. But in case of low density old dwarf, basically all the wind is very hot. And this means that it can leave just very weak observational signature. And actually, this could be the solution of this weakening problem, where these instabilities can really significantly affect what we observe from these stars. But again, I would say that the more research is needed in this region just to test these predictions. So to conclude, we have seen that to predict reliable muscle rate estimates from the theory, you have to use global unified wind models that basically somehow account for a unified interaction between the stellar wind and the photosphere, and basically describe smoothly the wind acceleration from the photosphere up to the supersonically accelerating stellar wind. There are a bunch of the models that do this. This means that account for the elastic line list and for the kinetic equilibrium equation to get the level populations that precisely solve the radiative transfer frequency by frequency, and consistently describe the transition from the photosphere and from the wind. And if you do this, then you can get quite good estimates of the muscle rate that somehow approach the observational estimates. But definitely, this is not the last word from the theory. Still, the journey is not over. Perhaps we will have to calculate the tailored wind models for individual stars. That could be complication especially for the evolutionary models. And maybe we have to will have to calculate consistent time-dependent simulations to really test that what is the influence of instabilities on the muscle rate. So thank you for your attention.
Okay, thank you very much, Jiří, for this very interesting overview talk and also the interesting results that you have presented at the very end. I'm sure this is going to lead to some questions and discussions. So time is up for question by the audience. Has any question? If not, maybe what people is thinking, I have, when you show this difference in the comparison of the predictions and the observations, when you were doing the calibration, you were using the calibration and the specific models. So could you explain a bit further what is the difference in the way you compute the two things. So
So
what
you
is
mean perhaps mean this two
this one?
this
Yeah.
one, yeah. What you can do with these Masaryk predictions is that you basically calculate some grid of wind models. So this means you vary the temperature of the star, luminosity, and the mass, and that gives you some kind of the grid of the models, and then you fit the models with some prescription. And so basically you get some function of the mass rate as a function of, say, star luminosity, effective temperature, or the mass. And then you can put in this in this function parameters of individual stars and compare with theory. And this is given in this graph. But you can you can approach slightly differently this problem. So you can really calculate wind model, basically the same wind models, but now for the parameters that correspond to individual stars. And this is given on this right graph. So now
Okay.
this is really calculated for individual stars, and perhaps this means that this fitting formula people are using to, for instance, in the evolutionary calculation, do not really affect for all effects that can influence the mass rate, and at the end, these tailored wind models calculate.
Okay, so this means that if you plot the fitting formula for a given set of models, and then you plot the results of the individual models, you also have there a scatter.
Yeah, exactly.
So this is like a very simplified fitting formula, no?
Yeah, the problem is that this fitting formula do not basically take into account all variations that can appear in the star in the stars.
Okay. So maybe it would be interesting to also think about how to, instead of just a simple fitting formula, to give like a calibration, doing with some taking into account also this scatter for later to be used as uncertainty.
Yeah,
Okay,
exactly.
thank you.
Exactly.
I can confirm this. We have also done this testing on our side with our common frame models, and we find the same thing. That the fitting formulas introduce a lot of scatter. In this case, it's the Björklund formula that we have, right? Yeah, that's part of the reason why we did our Sobolev base, but works fine. Line tool where you can get the tailor directly, right? Instantaneously, because it takes a long time to calculate the co-moving frame models, right?
I fully agree. If you look at all these fitting formula from different papers, and always there is a huge scatter, and it seems that this scatter seems to be real. Yeah, I agree.
So maybe it's good, even it's taking. I understand that it's taking time, but it's worth it to spend the time, and maybe in some years there will be like a better representation of this, taking into account the grid of models, or this is something that is no way to do this.
That's why I developed the line, or that we in my group developed the Lime tool, right? In the Lime tool that is online, you can actually just plug in the tailored parameters, including abundances, because Jiří didn't talk about CNO enrichment and stuff like that, right? But that also plays a role. To get it for that specific star, whatever star you want. And you can get it immediately. Of course, it would be great if we had common frame models for all. But yes, and if somebody has somebody who would be willing to work with, for example, me on our side, then I would be thrilled to do that. But they need somebody dedicated then who is willing to take up the task. I'm going to be honest.
Good to know both things, that there is a scatter and this is something doable. So maybe we go now to Andreas, who was first.
Yeah, thanks. Also, thanks, Jiří, for a very instructive overview talk. I would say this is makes it quite approachable, which is not always easy in this field, I would say. Yeah, also to this two-panel figure here, what was the main effect right here? Because I would imagine if this is typical LMCO stars, I wouldn't think that it's so much the abundances of the individual stars, but it's probably rather parameters that were not accounted for in your formula. So from your experience, would you say in principle we just need to add a few more terms to our formula? Or is it really such a thing that you need to go into the abundances, which is making the dimensionality almost unapproachable?
Yeah, the problem is that there are more effects in that. Already the abundances can cause some difference, but another problem is that you have, if you look at these stars, for instance, in HR diagram, then you can see that there is a scatter of the stellar masses, and some stars that have basically higher mass have lower luminosities and opposite. So there is a scatter of the stellar parameters itself and the metallicities. So all these parameters basically enter this scatter. So it could be very difficult to really calculate some grid because it would have to have a huge number of parameters. So yeah.
Okay.
Okay, Joe.
Jiří, thanks a lot for this very nice overview. And I just want to have one additional comment on this, namely, one of the major points, of course, to get more or less correct mass loss rates is how we describe the radiative acceleration in the sonic region. So, and when one compares, for instance, consistent or self-consistent simulations using co-moving frame transfer with those done by Sobolev, then one will see that particularly in this region, typically the velocity field, the final velocity field, is somewhat steeper than the Sobolev velocity field, and also then in this case that the mass loss rate goes down. So it's very important to have a consistent description in the sonic region particularly. And this is something which you showed in one of your first slides, namely the comparison between Sobolev theory and co-moving frame from this old paper by Adi Pauldrach and myself. And there it was clearly seen that in the wind regime, the Sobolev approximation is really more or less perfect. I mean, if one forgets about line overlap effects, but even those could be included in Sobolev. But then that just in the sonic region, we have a difference. And this difference, and this is what I wanted to point out, this difference is here, at least in this figure, due to two reasons. The one reason is that there is an impact on the more and more larger impact of the continuum radiative force, but also there is an important contribution because the velocity field has a curvature in this regime. Namely, at first we have something flat and then we have it steeper, and so we have a curvature. And Sobolev theory, at least in the standard way, does not account for such curvature effects. I have just recently tried to get a quick description including such curvatures, but it's finally a real mess to do all these calculations. So maybe one keeps this also in mind, that there is something really different in the Sobolev and the co-moving frame and the sonic point, whereas in the outer region the curvature effects are low, and therefore you see here an almost perfect agreement. So this is what I wanted to say. Thank you.
Yeah. Thanks.
John.
Yes, now I have the audio. Yeah, I 100% agree with what Joe said. The issue that we find in the last five to 10 years that we've been working on the on the turbulent simulations that Jiří showed Dwight-Payan, Dednat's results, of course, is that in this sonic region, so to say, which is the average sonic region, the velocities vary between like plus 200 kilometers per second and minus 100, say, kilometers per second for the stars that have significant line-driven winds. So we get in comparison to this dip, we get a significant smoothing effect, you can call it, right? And I've been actually pondering quite a bit upon what to do with that, because it's not trivial to do this with an observer's frame or a co-moving frame thing, right? It would be something like the walk-in pools formalism, escape integral formalism. It's doable, but it's very difficult. So I would say that is a really open question here now, because whenever you do a co-moving frame model, if you're being careful, you get this dip. I mean, you get the dip in this region. It's just like that. So you can't load too much mass. The question is whether it survives a turbulent simulation. And there, I honestly, I have no idea, if I'm going to be honest. But I'm just saying it that, yeah, some help here would be nice. Yeah.
Okay, any other comment, question? Fabrice?
Yes. Yes, thanks very much, Jiří. I had a question on one of the points you mentioned in the part regarding the weak winds. So you mentioned these instabilities that can create a very hot gas. And I know that there are some observational evidence for this type of gas. It's mainly from lines, as far as I remember, especially in Neon 5. I think that's detected now in a few stars. I was wondering if there is such hot gas at 10 to the 5K, do you think it would also affect the SED of the star? Or is it just too thin and the emissivity is too low? Because I think it could significantly affect basically the ionizing flux of the stars. What do you think?
Yeah, perhaps it can, but yeah, the winds are very tiny in this case, so I'm not sure how it would affect, but could be the case that also this can, in principle, influence the ionizing flux from the star. Yeah.
Mm-hmm. Okay, thanks.
Thank you. Any other question? If not, I want to have myself. Okay, so from your theoretical perspective and connected with the observations, things have improved a lot in terms of number of observations for different type of stars. So what will be your wish list to propose to the observers in terms of observation? Is O stars, different metallicity? I guess this is already there are already a lot. B supergiants, different metallicity, jump or going cooler to A supergiants. What would be your willing to compare with the predictions or to make some new developments?
Yeah, I will be
time series to see how is the impact of this variability.
Yeah, I think there are few more things that will be definitely interesting in this way. First, looking at metallicity slower than the SMC metallicity, because that's not that we do not have very large samples of these stars with very low metallicities. Then, as you mentioned, to look at cool stars like A supergiants, because apparently these stars also have some wind features, or may have some of these stars may have wind features. Some of these stars show magnetic field, so there could be some interesting interaction of the stellar wind and magnetic field. And there are also observations that shows that these line profiles are strongly variable, and this means that part of the scatter we have seen in this observational dependence of the mass oscillator on luminosity could also come from some time variability of the stellar wind. And I think this would be interesting to really understand how this affects some kind of mean mass oscillator. So this would be three observational views I would be interested in to look at. Yeah.
And then regarding this variability, is just enough to have like 10 data points covering different phases, or it would be interesting to see how's the variability and try to understand in more detail how this variability is happening?
Yeah, I guess you have at the end to get observation like it was this IAU mega campaign, I think 2 decades ago, actually 3 decades ago, that got a huge amount of IAU spectra of a single star. I think more samples like this would be very interesting with, say, HST to understand what really is the variability of these hot stars and hot star winds. Yeah.
Okay, noted. Also recorded for the future. Any other question, comments? Okay, if not, I think it's now time to say thank you very much again to Jiří. And thank you everybody for joining us. This is the last seminar of this season. Now it's time to rest a bit, and we will come back in September with a full list of new speakers and new topics. So I hope you have, if you're in the north, you have a nice summer break, and see you soon.
Thank you for coming. Bye.
Ciao.
Bye-bye.
Bye-bye, and thanks a lot for the organization and the talk.
Ciao, Joe. See you.
Bye-bye.